Sal
Thank, thank you, Petros, for the kind introduction. My name is Michael Möller, and I will briefly go with you to a short refresher of basics of tribology. Next slide, please. When we are talking about lubrication in modern machinery, then we have to think about really different things like materials in the machine, frictions, loads, wear, and many, many other things. And we really have to consider today that a lubricant is an important machinery element. Partly it can be calculated, for example, in some gears or bearings, but there are also many applications where bigger technical background is needed to find the right lubricant in place. And a small hint for you, buying a lubricant, often we are looking for the cheapest one which we can get, but this can get very costly. But on the other hand side, also the most expensive lubricant can be very costly when it's not the right one. So we really have to talk about which lubricant is, from the technical perspective, the best one for your application. Let's move to the next slide. Therefore, we have to consider a few basic things like contact areas and load in areas. For an example, we have taken two lapped and hardened steel plates of 50 to 80 millimeter, putting them on each other, loading them with a VW Golf, which has around about 1,300 kilogram or approximately 13,000 Newton meter. What do you think? How much of the area between the two plates is really in contact? We have looked through a good microscope between these two parts, and amazing, these are only 0.15% which are really in contact. Of the 4,000 square millimeters of the plates, this is an area of only 6 square millimeters. And this loaded with a VW results in round about 2,000 Newton per square millimeter pressure. Such pressures can also be found in some testings like FZG tests in the higher load stages. Next slide, please. To have a sufficient lubrication, we have to build in our machines a good lubrication film. And this depends on different things. Also, when we are going water skiing, we have to build a special fluid film under the water ski. Otherwise, the water skier will not have the fun he wants to have. Has to get the right speed to build the small hill under his water ski of water. And this is a lubrication film. When the speed decreases, this lubrication film will go down and he will sink into the water. So no more fun for water skiers. But replacing the lake from water to honey, it will be different. Then, because of the higher viscosity of the honey, the lubrication film will build up faster by lower speeds. This is also a hint for our machines and lubricants in the machines. If we have low speed applications, which are maybe also high loaded, then we need a high viscous fluid to build up the lubrication film right and fast. Otherwise, the other way around, if we have high speed applications, then the lubricant has to have a low viscosity to build up the lubrication film, because having a higher viscosity, it will be a very high lubrication film, and this leads into other problems we will see in the over next sheet. But now coming to some regime applications on the next slide. At first, having two moving parts to each other, the red one and the green one we see on the right side, in the boundary friction area, we more or less have no lubricant between these moving parts. This results in a high contact area when moving the parts, and also in high friction and massive abrasive wear. When the lubricant film starts to be built up, these moving parts are separately or partially separated by each other, but we still have some contact of the surface roughness. This results into medium friction and some abrasive wear. When we reaching the hydrodynamic lubrication film, we completely separate the both elements by the lubricant, and there is no contact at all between the moving surfaces. Therefore, we will get a low friction, and if the fluid is clear, then we have no wear in such systems. These regimes we will also find on the next slides on the Strybeck curve. Next slide, please. Here, there's the Strybeck curve. On the left-hand side, we see a high friction area where we have the boundary friction. Then in the second area, the mixed friction. And if we are increasing speed with the right lubricant, then we will get the hydrodynamic lubrication film, and we will have no wear. Looking on this sheet, we can see that an appropriate viscosity should be chosen to ensure hydrodynamic lubrication between the moving parts. Choosing a lower viscosity will result in mixed or even boundary friction, increasing wear and heat. Whereas choosing a higher viscosity than needed will result in higher fluid friction and maybe also in higher temperatures. High loads or shock loads may also result in mixed and boundary lubrication. Next slide, please. Talking a lot of viscosity, we have to know that the viscosity is the inner friction of the fluid itself. So molecules are flowing to each other, and this gives the viscosity of a fluid. In other words, is a resistance to flow. In the industrial lubrication world, the viscosity typically is given at 40 degrees Celsius and measured at kinematic viscosity with the unit square millimeter per second, which is 1:1, the older unit centistoke. So whenever you see on an old data sheet centistoke, it's 1:1 as square millimeter per second. But please be aware of the temperature. It has to be the same, because the viscosity of fluids is very sensitive. Taking an ISO VG 220, the 220 is square millimeters per second at 40 degrees C. But when measuring mineral oil at 100 degrees C with a VG 220, and you will get a result of 19. So the difference is very big with different temperatures. Sometimes also the dynamic viscosity is needed. Then you only have to multiply the kinematic viscosity with the density of the fluid. But please be aware of, you have to have the right temperatures for the density as well as for the viscosity. Next slide, please. Coming at the end of the short introduction, oxidation and oil aging due to temperatures. If we have a system running at, for example, 60 degrees Celsius for a long period of time, and the temperature will increase while something is changing at the system, up to 10 degrees Celsius, then the lifetime of the fluid will only be the half. There's a hint you can take. Every increasing 10 degrees Celsius will halve the lifetime of a lubricant. But not only temperature have an influence on the oil aging. On the next slide, we will see that also contaminants like water or particles of iron, of copper, it can be wear particles, for example, will influence the oil aging very hard. In first line, you see an oil oxidized at higher temperatures, but without water and any contaminant. It will reach a lifetime over 3,500 hours. But if you are looking in line 6, then you see there is copper powder in and water in the lubricant. We only get a lifetime of 100 hours, which is far away from 3,500 hours. And with this short introduction about basics of lubrication, I will hand over to Markus.
Thank you very much, Michael. My name is Markus Muth. I'm working for the Technical Support and Services Department, team leader there, and supervising the European and African markets. I'm going to tell you a little bit about our PD technology, laboratory tests we do for that, and later on also how this will influence CO2 efficiency and energy efficiency in your components. Next slide, please. Here we will see a short video showing you how PD technology, plastic deformation technology works and what it can do within your machinery.
Everyone in the industrial sector is seeking new advantages and improvements to deliver ultimate operational effectiveness. Industrial lubricants are supposed to protect your key components from wear, minimizing unplanned downtime and maintenance costs. But within conventional lubricants, the lubricants' additives are sacrificial. They get used up and need to be replenished. And even though they protect your equipment, there's still wear, and breakdowns eventually happen. To understand why, let's take a closer look at the metal's surface. Under the microscope, even the smoothest finished metal looks like this. With conventional lubricants, a small minority of the surface area supports the entire load. More pressure, more friction, and more damage. Conventional lubricant additives protect these contact points by forming a protective layer. But the top layer is continually worn away and damage still occurs. Fresh additives need to form a new layer and additives get used up. The more damage and pitting there is, the worse the problem gets. Castrol's microflux transplastic deformation technology and TGOA additives take a different approach, called plastic deformation. It actively smoothens the surface without depositing or removing material, rapidly providing a protective layer with a high lubricating effect. With increasing load, this protective layer is compressed, becomes even more pressure resistant, and at the same time improves the coefficient of friction. As the pressure increases further, special additive components migrate from the deposited protective layer into the structure of the metal surface, initiating the micro-smoothing effect. The micro-smoothing multiplies the load-bearing surface area. That means less pressure, less friction, and less wear. And the lubricant's additive and non-sacrificial, so you don't need to replace the lubricant so often. The result is increased protection and lower maintenance, lower energy and lubricant costs, and less unplanned downtime. Equipment lasts longer and can work harder, making you more productive than ever. Castrol products with MFT-PD technology provide best micro-pitting resistance when compared to the global market leader's product. Castrol's MFT-PD technology is in use now with impressive results at plants all over the world across different business applications. If you'd like to find out what it can do for you, talk to your Castrol lubricant specialist. Castrol MFT-PD technology. Find out more at www.castrol.com.
So this is basically how you can visualize plastic deformation technology to work. It helps you to level out the surface roughnesses, which are responsible for the low load areas that Michael has talked about. What does it do? What are the benefits of plastic deformation and of optimizing your surface, making it smoother? There are lots of benefits, and we could just list them down, but I always find it a little bit easier to understand if you break it down into something like a cascade. So the basic thing we do is we are able to smoothen the surface, therefore reduce the roughness, and this has two effects. It increases the load-bearing capacity, so the load is more evenly distributed among the surface, and it lowers the friction. It lowers the friction because the interacting surfaces, the surface roughnesses that interact with each other, are the ones that create the friction between the friction bodies. What does increased load-bearing capacity mean? It means you have increased component safety. I think the slide was excellently swapped around. Increased load-bearing capacity should be on the right. It increases your component safety. Because you have an increased component safety, it reduces your downtime, increases the component life, and slows down the damage progression of pre-damaged components. Just imagine a gear flank which has pittings on it. Because it has pittings, there are parts of the surface missing, and less surface is available to get in contact with each other. Because there is less surface, the tension, the stress on the surface will increase because it's distributed amongst a smaller surface. Now, if you're able to increase that by increasing the improving the surface smoothness of the rest of the surface, you can lower down that stress again, and therefore increase component safety and lifetime, even for pre-damaged gears. We will see that in another test later on. Lower friction, on the other hand, increases the energy efficiency. So you get lower energy costs. You can directly save money there, and it lowers your temperatures. Lowering temperatures has a multitude of positive effects. It lowers your oil cooling costs. We have had cases where customers were able to even unmount their oil coolers. Now just imagine not having to pay any energy costs for your oil coolers anymore. Might be extreme cases, but they're real. We have experienced them. You can extend lubricant life, as you have heard in Michael's presentation part. If you reduce the oil temperature by roughly 10 degrees Celsius, you're going to roughly double your oil lifetime, just talking about the oxidation of the oil itself. You increase also your component life. Just think of rubber components, all your seals, for example. They're also very depending on temperatures, and an increase in temperature also lowers their lifetime. Especially during run-in periods, you can have a very high peak temperature within your components, way above what you typically would experience in a normal running condition, which can have significant impact on your overall lifetimes of the seals, for example. And if you're able to reduce that by 20, 30, 40 degrees during the running process, which we can also see in our test environments, then you have a massive positive impact on those components' lifetimes as well. Of course, if your lubricant is able to last longer because you were successfully able to lower your oil temperature, you have to replace the oil less often, so you have reduced maintenance cost, reduced man-hours cost, and of course have a higher efficiency of equipment because it runs for longer and needs to stop less often, and therefore you have reduced downtime. Overall, this results in greatly reduced maintenance costs. Next slide, please. When do you use PD technology? Are there some indicators which help you to identify equipments or applications where PD technology could be of benefit? The most important ones to look out for are, of course, number one, the mid or highly loaded components that you use. So everywhere where we have load, you potentially or most likely need additives like extreme pressure additives, anti-friction additives, and everywhere where you use them, where you can benefit of their existence in the oil or lubricant, you can benefit from the PD technology benefits as well. The second one is if you have very high temperatures in your system that are not created by the surrounding, for example, radiant heat of an engine or heating or something like that, but comes from the friction inside your component. You can, with PD technology, in many, many cases, reduce the friction and therefore the temperatures. If you detect damage in your equipment, it is most likely due to a high stress, due to an overload, due to mixed and boundary lubrication. And every time you have mixed and boundary lubrication, you have interacting surfaces, metal surfaces, you need additives. And whenever you need additives, PD technology will give benefits to you. And of course, wherever you need high equipment availability. As I've mentioned before, PD technology can help to increase component reliability by distributing the stress more evenly, therefore making it safer and longer lasting. So if you want your critical equipment to be up and running more often, more safely, it could be very useful to consider PD technology for that equipment. Next slide, please. We have done, as I mentioned, many tests, and we have a lot of field experience, actually multiple decades now with PD technology, so we know what it can do, but we always strive to test it more to the edge, really get it into boundary conditions and really demonstrate what it can do compared with conventional additives like zinc-tiophosphate, like phosphor, sulfurous additives, and so on. And one of the test rigs that I really like to demonstrate is the MPR test rig. What does MPR test rig do? It's basically a very intense screening test for gray pitting, gray flecking, micro pitting. It is deliberately designed to cause micro pitting on a surface and therefore able to create micro pitting in a very short time. So typically in a classical micro pitting test rig, you have 6 times 80 hours endurance test stages, so quite a long time, and you get a similar effect in this test rig within 24 hours. So greatly reduction in time. It kind of demonstrates already the stress that the surface is put to. Next slide, please. We have tested a total of 3 lubricants in this test rig. All of these lubricants are synthetic ones, PIO based. All of them have a very high micro-pitting resistance according to the data sheet. So in a classical test, they have a failure load stage of greater 10, so appear to be equal. And we have run in total 3 steps, so 3 repetitions of the test to make sure that it's not a one-time effect, but we can see it in all 3 repetitions of this test and know the results are very reliable. Next slide, please. Here you can see the roughness of the test roller, the surface of the test roller. The surface that is in contact on here is roughly 1 millimeter wide. In the upper image, you can see a competitor grease. Again, this has a high micro-pitting resistance. But at the end of the test, you can still see micropitting on the surface. Again, this test rig is designed to create micropitting. On the other hand, if you use a PD technology product like OptiGear Synthetic PD 320 or the new version 320 ES, you get a very smooth surface. It's very shiny, very flat, and there's no gray flecking at all, even after the last load stage. Next slide, please. To give you an even better image, we have recorded the surface with a microscope. You can see the scale on the screen. So the area that is shown in the lower right corner of the left-hand picture is roughly 100 microns. The surface roughness has roughly 200 nanometers originally, and then you put the test through 3 load stages with increasing loads between each stage. As you can see with the competitor ones in the middle and on the bottom, you can see a greatly changed surface in load stage 2, latest in load stage 3, with a lot of surface roughness appearing. And this surface roughness that you can see in this recording is the gray flecking, the micropitting that you can see. The upper line is the synthetic PD 320S product, so our PD technology one. And as you can see, the surface appears even smoother and even and more even than the original one before the test. We can demonstrate this also in other recordings on the next page. Here you can see the PD product on the left-hand side. You also see the surface roughness measurement. Remember, the original state was 200 nanometers. After those tests, PD technology was able to reduce the surface roughness to 42 nanometers. Whereas with the other conventional products, which again also have a high load carrying capacity, a high micropitting resistance, increased surface roughness to roughly 350 nanometers, or with the second product, up to 650 nanometers. And there you can see the difference. Even though on the data sheet they look the same, PD technology behaves different in this very stressing environment, and that's where you can create your benefits. Next slide, please. This is another test rig that you might know. This is a FE8 rolling bearing test. So typically you put rollers in there to test for wear and also for friction, the torque that is generated within the system. And what we have done here is we have prepared 2 oil sumps with 2 different products. One is a conventional high micropitting resistance product that is used in the wind sector, and the other one is a synthetic PD 320 ES with PD technology. What we wanted to test is how do they behave if we change them during the test. So we just swip a lever, and then the oil flows into the bearings from the other oil sump. And as you can see, whenever we switch from the competitor one to the PD product, the torque greatly gets reduced. This is the red line you can see. Aligned with that, also the temperature decreases. So as soon as we switch to the PD product, within very few hours, the surface seems to be optimized. Friction gets reduced, temperature gets reduced, therefore potentially your oil life increased and your energy consumption reduced as well. The next step was to swap back to the competitor and see whether the improved surface will prevail and still give the benefits to the component. This is not the case. As soon as you remove the product with PD technology, a typical lubrication layer, a typical EP or AW reactive friction layer will form on the surface and will not protect the surface similarly than PD technology will. So it's reversible. This effect is reversible. Going back to the PD product, you can see a drop in the torque and in the heat again. So if you want to benefit from the PD technology over time, you will need to keep the PD product running. Next slide, please. You can not only reduce your energy consumption with PD technology, but you can also stop damage progression. If you go to the next slide, please. you can see a typical micro-pitting test recording. What we have done is we have gone through the initial load stages with a very bad oil, so a high, or not a high, a low micro-pitting resistance, resulting in high micro-pitting area. So we have purposely, on purpose, created a pre-damaged area in this test rig. And then for the later load stages, for the endurance tests, we have swapped to other oils. One time to a high performing lubricant with conventional technology. So with, for example, phosphorus, sulfurous components in there, but with a high micro-pitting resistance on the data sheet. And the other time, in the other test rig, we have used a PD technology product instead. And what you can see is that even though you add a high micro-pitting resistance product with conventional technology, the damage progression still goes on. And we ended up at roughly 70% of the surface being affected by micro-pitting. Whereas with the PD product, the damage progression was severely slowed down. And while we had 22, 23% pre-damaged area in the beginning, we ended up at only 28 in the end. This clearly, again, separates the performance of the PD technology from conventional ones, even though on the data sheet they look the same. Next slide, please. Next, I would like to talk to you about energy efficiency and CO2 reduction. Next slide, please. So how can you influence the energy efficiency and the energy savings in your components? The first thing you can do is make sure that you have the right viscosity for your application. So as Michael described earlier, if you go too high in viscosity, the inner friction increases. Therefore, you get higher friction, need more energy to really churn the lubricant around. On the other hand, if you choose a too low viscosity, you will end up with mixed and boundary lubrication, therefore interacting metal surfaces, therefore increased friction and also wear. So ideally, if you want to save energy, you try to select a lubricant that has a viscosity right around the separation spot. So we just barely are able to generate a lubricant, a fluid friction film, able to separate you both friction surfaces. But unfortunately, that's also not always possible. So what can stop you from selecting a viscosity that's right for your application, that's always fitting? Well, for example, transmission in your gearboxes. If you have a transmission in your gearbox, you have a multitude of speeds. You have low speeds in the beginning and high speeds at the end, or vice versa, and therefore different speeds within your contact areas. Therefore, you cannot ideally select the viscosity for each one of those stages. The next one is if you have a change in temperature. As Michael also said, a change in temperature has an influence on your viscosity. And if your temperature changes, your viscosity will change, therefore your energy efficiency. If you have an application that has changing speeds, potentially also stops and starts again, lots of stop-start actions, or has reversing directions to go, you will also always run through boundary and mixed lubrication conditions. And you will not always be able to generate that fluid lubrication film that will completely separate your surfaces. And these are the times when you can really benefit from additives in your lubricant. Whenever you have the opportunity to constantly separate your surfaces by choosing the right viscosity, this is the best thing to do. Select the right viscosity and everything's fine. But if you can't, if you do get mixed and boundary lubrication, and in most cases you will, then you need to rely on additives. And there, as we have seen before, PD technology can do a whole lot for you. They are able to increase the load area, therefore reduce the friction, reduce the temperature, and therefore influence your energy consumption, or increase your energy efficiency and reduce your energy consumption. Next slide, please. What about CO2? Basically, it's the same for the CO2 reduction. If you reduce the energy consumption of your application, you also reduce the CO2 footprint. Of course, based on your electricity mix. If you're purely powered by renewable energies, of course, your CO2 footprint will be next to none. But if you rely on conventional energy that's made out of gas, out of coal, out of wood that's being burned, and so on, you will have a CO2 footprint. You will have a CO2 usage. If you're able to reduce the friction in your system, increase the energy efficiency, you will also reduce the CO2 that you produce within your equipment. On top, there's something else that you can do to lower your CO2 footprint, and this is expansion of your lubricant change intervals. So the longer your lubricant runs, the less often you will need to change it. And since it's most likely based on mineral oils, you have a positive influence on your CO2 footprint if you're able to extend that interval. Next slide, please. Here we can see a live result at one of our customer sites. They have chosen one of their permanently running equipments. They have done an intensive test, not with just 2 products, but with many different ones, playing with viscosities, playing with additive systems, playing with base oil types. And here you can see that compared with the original product that was in there, a standard 220 viscosity grade gear oil, we were able to save roughly 9% of the energy this equipment needed by swapping to a PD technology gear oil. It's the same viscosity, both of them are mineral oils. The only difference is the PD technology within our product. And this was the product that generated the highest energy efficiency within that equipment, which was also fit for purpose and fit for application. In a total, we were able to save roughly 2,200 kilograms of CO2 just in this single equipment within the duration of one year, so 8,000 operating hours. Next slide, please. On top, if you're able to double the oil life and replace it only 50% of the time that you currently run it, this equipment would save an additional roughly 1.3 tons of CO2, 1,300 kilograms. How can you do that? How can you extend your oil life? For one, by reducing the temperature. If you swap to a PD technology product, we know that in many cases we get also a reduction in temperature. Again, 10 degrees C, double roughly your oil lifetime. You could go from a mineral oil to a polyalpha olefin. This will also roughly double your oil lifetime at the same temperatures. And you can support this with regular oil analysis. So whenever you have constant monitoring of your oil and know when to change it, and just change it on demand, not by a given timeline, you can also optimize your oil change intervals. And I think I'm done with my part. Next slide, please. Yes, handing over to Daryl.
Yes, thank you, Marcus. So good morning, good afternoon. I'm Daryl Luke, Global Product Manager for Industrial Oils, and I will take you quickly through the gear oil product range. So first, let's look at the Castrol main ranges. Essentially, we have them split here into 3 categories. We've got mineral oils, synthetic polyglycol or PAG, and synthetic polyalpha olefin or PAO. In terms of the products, we have general industrial or GI. They tend to be branded Alpha or Alpha Syn, and we have high performance lubricants, HPL, called Optigear or Malubaloy, all with different attributes and performance characteristics really. So information, more detailed information about these products can be found on our Lubricant Oracle website, and even more detailed information on high performance lubricants can be found in our digital HPL guide. Today, however, we will focus on Optigear BM, Optigear EP, and Optigear Synthetic PDES. So let's first look at the first product range, Optigear BM. And on the next slide, I've included a description of the range. It's Based on microflux trans plastic deformation technology, which we've heard about, provides gear service smoothing effects, low friction, and high micropitting resistance performance. It is Flender approved as well, and due to the low friction, it can also be used as a slideway in slideway applications and can provide energy savings. Phil Booker will go into more detail for OptiGear BM and how it relates to total cost of ownership. So PD technology is a fundamental part of OptiGear BM given its low friction. So if we move to the next product, because Phil will cover this in more detail, OptiGear EP. Again, I've included a description here. So OptiGear EP is essentially like OptiGear BM with the PD technology, plus it has extreme pressure EP additives, load carrying additives on top. Now the combination of the plastic deformation technology and we do the automotive GL5 FZG test to give an indication of that high load carrying. If we recall from the famous Strybeck curve, OptiGear EP is good for applications where boundary type lubrication occurs, such as start-stop motion as in robotics or textiles. To highlight the load carrying on the next slide, we see the FZG sprung test or jump test. This relates to the automotive GL5. It's different if you look at the attributes there on the right hand side of the test. It's different to standard industrial FZG load carrying tests in that it's directly run at high loads, no running in. It has smaller gear teeth, it's double speed, and it runs backwards. In the pictures on the left, you can see a conventional general industrial type of gear oil. On the right, you can see OptiGear EP, where even the original machining crosshatch marks can be seen. So why don't we use an automotive type of gear oil? Well, on the next slide, it has been mentioned the FE8 bearing test. So for an automotive GL5 gear oil, it can generate up to 100 milligrams of wear or more. And for a DIN CLP gear oil, you need lower than 30. And DIN CLP is a requirement for the majority of industrial gearbox manufacturers as a minimum. OptiGear EP gives around 10 milligrams of wear in this test. Not as good as OptiGear BM, but still pretty good considering the load carrying I mentioned on the previous slide, and certainly qualifies as a DIN CLP gear oil. I will go through a few examples where OptiGear EP has been used or approved. So on the next slide. So we've mentioned Brugger several times, which is another load carrying type of test. For Schuler presses, for Schuler press approval, a value of greater than 50 Newton meters is needed, with OptiGear EP at 60. We're just waiting for the approval documentation to come through for Schuler approval, but we have the approval. We're just waiting for the documentation to come through. So high load carrying in these Schuler presses. Another application on the next slide is the relatively small planetary gearboxes, which go through a lot of start-stop motion and switching and need to be very accurate over the lifetime, so minimum backlash is required. OptiGear EP was tested in long-term field trials with excellent results in these gear types. Turning to a different application, in this we see an open cast mine, totally different application to those smaller planetary gears, where the gear at the bucket wheel is under very high loads and had a tendency to pit. With OptiGear EP, any new pits were minimized, and the PD technology even helped to smooth existing pits caused when the previous lubricant was used. So a very different high load application. On the last example for OptiGear EP, this is in railway gear units. I almost think of them as a mixture of automotive and industrial gearboxes. Formerly, we had the OptiGear range there, which has been upgraded to OptiGear EP, And in this test, you have a mixture of both high load carrying and bearing performance. And the OptiGear EP has very good yellow metal compatibility. So that was just a quick snapshot of OptiGear EP. We have a lot more information on that. If we go to the next slide, I'm going to move to the OptiGear synthetic PD range. And on the next slide, I have a description of the range. So it's synthetic PAO, as the name implies, and it's coupled with this microflux trans plastic deformation with low friction properties, and it's also Flender approved. The technology was developed really from our experience in the wind sector, with a very stringent specifications and application requirements of that area. We've actually got up to 30% lower frictional torque compared to conventional or other lubricants, certainly potential for energy savings, which is where the name comes from, ES. So on the next slide, and we have a lot more properties on synthetic PDES, but really just pulling out two of them here. So oxidation, which has to be good to justify the use of a synthetic. In this, we check the viscosity change, any residues formed, checking both the base fluid and if the additive system itself can protect the base fluid and withstand any high temperatures. Also highlighted is the FDA bearing test mentioned, and this highlights any wear or any frictional torque. And as you can see, we've compared to several competitor oils. So PDES actually performs very well, which is where we focused on oxidation and bearing wear. In the next slide, we've pulled out the frictional torque in more detail. In the graphs, you will see the blue line for frictional torque, all on the same scale with the numbers in the table. Where PDES has up to 30% lower frictional torque than other commercially available oils. Even some are marketed as advanced or high performance. So exceptional low friction, which can provide potential energy savings. On the next slide, it highlights what the low friction can do. So in this example, 4 auto mills were identified and monitored for energy consumption before and after changing to OptiGear synthetic PDES. The customer in question actually used an external company to carry out and ratify independently the results. The lower friction translated into lower energy consumption. Enough energy was saved equivalent to probably power 250 households for a year, and saving monetary wise about 13,000 euros per month. So an analysis also showed lower wear metals with PDES, indicating better protection of the gear units. So a real example where PDES can save energy. On the next slide. Another possible, more poignant example was in this already damaged gearbox where the replacement parts were not available in this conveyor gearbox. The customer in question switched to PDES in order to prolong the gearbox life as much as possible until the parts arrived. Essentially, PDES kept the gearbox running for 4 months until these replacement parts arrived and could be repaired in the planned shutdown. Had the gear failed, this could have cost about 78,000 euros per hour in lost production. The extent of the damage was only really realized when it was open for maintenance. You can see the picture of the state of the gear teeth on the left there. So even PD technology, we do say how good it is, but even this couldn't smooth the effect of the surface of that gearbox. But at least it kept it going till a maintenance interval, and we had the customer had the spare parts. So a bit more poignant where parts are not as readily available at the moment. So another example, both energy saving and also, to the next maintenance shutdown. I will now pass over on the next slide to Phil Booker, who will go through total cost of ownership using OptiGear BM as an example.
Thank you, Daryl. Hi everyone, my name is Phil Booker. I'm an application engineer working globally with what we call our HPLs, High Performance Lubricants. And also the way that we apply them is through what we call TCO, which is total cost of ownership. And that's a term that you may be familiar with already. Slightly different for our perspective from a lubricant provider and solution provider, because we look at it from the lens of the lubricant itself, first of all. So to explain what this slide is showing, first of all, at the bottom there, we have where our TCO focus is. So in the red is a traditional lubricant supplier. They're interested in what the current lubricant is, so they can provide a very similar product. Whereas what we look at is, well, first of all, is it the right product? Is there a better solution? Since that lubricant, so if it's a gear oil, has been put in place, it could have been many years ago since the lubrication requirements were last looked at. If speeds and temperatures, loads have changed since the equipment was installed, and that's quite likely because most production units are designed to have a bit of spare capacity, but then once the units get older, capacity goes up even further, and the equipment is running beyond its designed capacity, but the lubrication requirements aren't seen as that important in general. So if we look at the total impact on the process of what is the impact of that lubricant on uptime, equipment life, extending asset life, and so on, and that's what we call total cost of ownership. So the pie chart in the top right corner there shows what a typical maintenance budget looks like. And globally, the actual spend on the lubricant is typically between the range of 3 to 5%. And that's through a number of different studies and a number of different industries. The red section, replacement parts, that can be influenced by having the right lubricant. Maintenance labour costs can also, to a certain extent, be influenced by the lubricant choice. There are some parts of a maintenance budget which are outside of that scope, obviously. So if we go to the next slide, please. This shows that pie chart in a slightly different way, so stack chart instead, and we can see where the costs due to inappropriate lubrication are. And that's a result of not using the right lubricant at the right time for that particular application. And if we don't have the right lubricant for the right application, then we have additional costs, the downtime, maintenance, labour, spare part replacements, and so on. So all of that is within that green section at the top of the stack chart, and it can be influenced by the grey section just below it, the cost of the actual lubricant itself. Other costs we cannot influence. There could be mechanical fatigue, assembly, etc. So next slide, please. Thank you. Now, if we concentrated just on the cost of lubrication, so if, as a lubricant provider, yes, we realise that cost is important, not just cost of equipment, costs savings, but cost of the actual lubricant itself. So if we offered a 10% reduction, then the overall cost difference to that entire maintenance budget would be minimal. It could actually mean that the costs go up because offering a cheaper lubricant means that maybe the machinery isn't being lubricated as well as it could have been previously. Next slide, please. So what we like to do is look at total cost of ownership, and if we can reduce that cost of inappropriate lubrication by focusing on appropriate lubrication, then that's the way that we can really add value. And you'll notice there that lubrication costs aren't higher than the original 3% on the first slide. So what we would look for, if it's grease lubrication, to optimize the grease consumption. If it's gear oil, then we would look to make sure that we could extend the life of the gear oil, perhaps, to make sure that the cost of the lubrication is if we can possibly make it no higher than what you're currently paying. And the way that we can do this to reduce, really reduce that cost due to inappropriate lubrication is to understand the lubrication requirement of each machine. So gearbox, we look at the gear teeth plus the support shaft bearings. It could be any part of machinery that we look at, and we'll look down to the basic component level. Next slide, please. So it's really important for us, and this has been mentioned more than once, even just in this presentation, to think about the principles that are described in the Strybeck curve. So where do we want to be? Well, ideally at the point of lowest friction, certainly away from boundary lubrication, where you have direct metal against metal contact. And to get away from that, we need to either increase the viscosity, or if the load is still too high or the speed is too low still, or if it's a reversing speed, then we have to think about the type of additives that are used within the lubricant. And we've talked a bit about some of the additives today. And that's where I'm going to move on for the next slide, please, where I'll talk about a case study, which was within a steel plant in Eastern Europe. And the plants were kind enough to let me share this information. So basically, this is within an area of a steel plant called Long Products. So it's after what's known as the melt shop area and downstream of the continuous caster. So in this case, they're creating I-beams, structural beams for houses, construction industry, and so on. And after these have been processed through the rollers, they're cut to certain lengths before being shipped out to end users. They're cut using cutting wheels, more than 2 meters diameter, very simple, almost agricultural operation where there isn't any direct cooling or certainly not cutting fluid. There's some water involved, but mainly these cutting wheels are just run through these I-beam sections, and many times during each shift, etc. And eventually the gearboxes break because there's too much shock loading there. So to give you an idea of what that application looks like, we can go to the next slide, and there's a short video. Thank you. Thank you. Next slide, thanks. So looking at that application, which was a simple bevel one-stage gearbox with support shaft bearings for each gear shaft, with quite a large motor mounted directly to the gearbox, which in turn was mounted on the output shaft directly to the cutting wheel. The current oil grade was given, which was 320 millimeters square per second, or 320 centistokes. And under normal conditions, doing calculations for the gearbox requirements, that should give enough lubricating film thickness to separate the metal surfaces. It's due to the very high shock loads that you need a gear oil with high performance additives in that particular application. Now, the current or the oil that was in place didn't contain any solid film additives or oils with plastic deformation additives either. So the lubricating film thickness wasn't sufficient to prevent damage and reduce the life of each gearbox. Now, a good gear oil should last for at least 4 years, really. We've seen through what's known as the Arrhenius equation, which was the effect on each 10-degree rise above 60 degrees centigrade on the oil life, the oil life will half above 60 degrees if it's a mineral oil. So the application was pretty much at ambient temperature, so there's no need to, in this case, choose a synthetic base. One key thing to remember and to consider is that the lubricant needs to be fit for purpose. So it wouldn't be useful for me to go along and for every application I see, just choose the absolute best lubricant, because that lubricant, a lot of its attributes would not be used. So it needs to be fit for purpose. In this case, no need to spend the extra money on a synthetic oil, just use a mineral oil. The important thing here is the additives. Now, what we could have done is perhaps considered increasing the viscosity quite a lot. That could have been possible, but for one thing, because looking carefully at the engineering drawings and inside the gearbox as well, we had a chance to. The gearboxes have a circulating pump system and sprays. Now, in that case, it's really important to try to match the current oil viscosity, because if you don't, then you will alter that spray formation, and you could find that you starve parts of a gearbox with the lubricant. The fact that we could choose a mineral oil meant also that it's compatible with the current product, which was at the time a mineral oil anyway. So next slide, please. So after we changed over to the Castrol OptiGear BM320, which is 320 centistoke base oil viscosity, contains that plastic deformation additive that you've seen from the video previously. So what it does is smooths out the surface, means that you reduce the height of that surface roughness, so the film thickness is larger than the surface roughness. Once those peaks have been smoothed out, you end up with a larger contact surface area that the base oil itself is able to support and not let metal-to-metal contact occur. So what does that mean? In reality, what it means is that your asset should last for longer. What we can see here is if we look at L1 to L5, they are points where vibration analysis are taken. So L1 and L2 are motor indirect and direct points. L3 is inside the gearbox on the first shaft, first support shaft bearing. L4 and L5 are the output shaft support bearings, where L5 is nearest to the shaft end that's connected to the cutter. And then we have the three axes that we take, horizontal, vertical, and axial. And we can see from that table there that if we just concentrate on L3, L4, L5, because they are influenced on the type of gear oil that's in use, whereas L1 and L2 are the motor bearings, so they're not lubricated by the gear oil. We can see L3, L4, L5 over a period of 3 vibration analysis measurements. We took 1 before and 2 after. We can see that there's a definite trend downwards. So we're reducing the peaks of the vibration analysis, and that's a direct result of that smoothing effect of the plastic deformation additives within Castrol OptiGear BM320. So if we go to the next slide, please. Thank you. We can see inside the gearbox there, it's not a great picture, and it doesn't really show us much apart from the fact that we would expect this type of gearbox being very robust to last for a long time. The gearboxes only lasted for 6 months before they would break, and they would either need refurbishing in situ, so in place, so the machine has to be shut down, or they would need to be taken out by crane and then stripped in the maintenance workshop on site. And that could be a complete replacement of the gearbox if it had destroyed itself, or it may mean just replacing one support shaft bearing. But in each case, on average, every 6 months, one of these gearboxes would fail for some reason. There are 5 of these cutters on site, all performing the same task. It's not the case, though, that you take one out, you still have production at 100% through the other 4 cutters, because these failures were so frequent that they couldn't have enough overall equipment effectiveness, OEE. So the uptime wasn't able to keep up with the demands of production requirements. Next slide, please. So here we have some figures. This was quite some time ago, so maybe the figures aren't relevant in themselves, but the fact that it's an 83% saving on what the previous total cost of ownership costs were. All the costs are in there. In this case, yes, the oil costs slightly more, but not that much more, really. When you think the significance of certainly the impact of downtime, manpower costs, spare part costs, etc. So with these 5 cutters, yeah, €500,000 per year saving, which, yeah, it's a number, maybe different on different sites, but because we had more than 80% savings on the total cost of ownership costs, this was seen as a good success where, as I said, the customer was happy for me to share this story. So thank you for listening. And now I believe we're over to the question and answer session. So please, if you do have questions, let us know. So you can put them in the chat box that you should be able to see in front of you on screen. And I believe we have a couple of questions. So I'll hand over so these questions can be answered. Thank you.
I think, first of all, I would like to thank all the speakers for their sessions. I think we have in the row 2 questions, mainly directed to Marcus. So, Marcus, could you please take the lead?
Gladly. Thank you, Petros. Just a short reminder, please do feel free to add in any more questions that you have. We will try to answer all the questions that come in via the Q&A text box before the call closes. Also, if you want to give us feedback, please feel free to do so scanning the QR code that you see on your screen currently, or by clicking on the link that will be present in the documents that we can circulate. The first question from an anonymous visitor in the call: according to your experience, how long would it take to see the differentiation in performance when a special additive lubricant is being used in comparison to a conventional one? I'm assuming this is regarding the MFT plastic deformation technology. If you remember the slide where I was talking about the FE8 test rig, you could see that the total span of the test was 500 hours. And when we were swapping from a conventional additive system to the PD additive system, the drop in the graph was also was very steep. So looking at it or magnifying it, you could see that it's less than, I don't know, it's hard to say, but 2, 3, 4 hours, something like that. So very, very fast. And if you imagine, for example, the case where we have seen the pre-damaged gears that Daryl has been talking about, if you have a gearbox that's damaged to that point, the failure is almost imminent. If the additive system would take a long time, a couple of days, weeks, months to even show its benefits, the gearbox would not be able to be saved by the lubricant. So again, there is a strong indication that the effects kick in very, very rapidly. We know from experience and also from other tests that we can see differences right at the start. We can see differences already in running in processes. So if we, for example, check the temperature, the torque, or the friction in our tests and monitor these, we can see that the run-in period is shorter than typically. The temperatures are 30, 40, 50 degrees Celsius lower from the start. That friction is lower from the start. So the effects can happen very, very fast and immediately, and even have a positive effect during run-in periods, for example. Of course, it's hard to say how fast it will be in your specific application. There are many things to consider, like the load, the speed, the temperature, and so on. If you have a system that in most of the time runs in the fluid friction condition, so with totally separated surfaces, the additive system won't work because there is no contact between the areas. But you also don't need the additives in that condition. You only need them in mixed and brown tube applications. And if your equipment only occasionally gets into those areas, you will have a lower benefit from the PD technology or any other additive technology. Therefore, it's highly dependent on the system. But when you need it, when you want it to work, it is typically there from the start within a very, very short time. I hope this answers your question sufficiently. If not, please feel free to put in a follow-up question.
Yes, please.
Petros, please continue.
No, I would like Phil to give an answer in the question. Are there any instances where PD technology can cause harm to the equipment?
Yeah, thank you very much, Petros. So there is one specific example that I can think of from a practical perspective. Depending on the type of gearbox that you have, sometimes you have things called internal backstops present. Now, a backstop will prevent the shaft from rotating in the wrong direction. So it's a bit like a freewheeling or overrunning clutch, if you like. You quite often find in the literature for backstops and their operation not to use friction modifying gear oils. So this is quite important that in that case you are limited really to conventional sulfur and phosphorus protection within the gear oil itself in terms of additive. Because if you use a friction modifying gear oil, then that clutch assembly may not work, and you could find that the backstop itself will then allow the shaft to rotate in the wrong direction. So it depends on the equipment if you do have one of that type of clutch installed within your machinery.
Great, thank you.
Yeah, and Marcus, I believe you're going to start with the energy saving. I'd like to add to something afterwards as well, please, if I may.
Okay, there's another question which I accidentally completed that I would like to pick up before. It was asked, is there any enhancement of the additivation required for this type of lubricant, for example, topping up in certain intervals? Typically, no. As you have heard in the video, the PD technology is non-sacrificial. So typical additives like phosphorus and sulfurous additives or zinc phosphate would build up reactive layers on top of the metal surface, interacting with the metal surface. They would be sacrificial, worn off instead of the metal surface, and used up over time. So they're depleting, and you need at some point to replenish the oil, fill it up with new one, change the oil, etc. With PD technology, we quite often see a stabilization. So you have a consumption at the beginning, the lubrication layer that's protecting your surface is built, which is why the additives lower down in your oil analysis, but at some point they will level out and they will not be fully static, but the usage of those additives will slow down significantly and stabilize over time. We have many operations where those type of oils last for years and even longer. We have cases where we, for example, in railway gearboxes with 50,000, 60,000 operating hours without an oil change and the additive system still protecting the gear, putting it back on the test rigs, this used oil still getting the original results we generated regarding friction and wear. For one of our wind gear products, we have recently introduced additive package to top up the wind gear turbines with additives specifically used in this oil, but in the industrial sector, We have not introduced such a product, and so far I'm not aware of cases where this is frequently needed or required. I hope this also answers your question sufficiently. The next one, as Phil said, is about energy savings. The question is, which is the typical percent in energy savings from a synthetic oil with PD versus a conventional mineral oil? The answer to this isn't really static. Again, this depends quite a lot on your application and the conditions that your application runs in. If you have a lot of boundary and mixed lubrication and therefore profit from an additive system quite a lot, from a good, advanced and sophisticated additive system, you will get more benefits. If you have a lot of stop and start action, if you have different speeds and so on, you can benefit more from the additive system than a system that runs quite frequently in a state of hydrodynamic lubrication films. Because if there is no interaction between your metal surfaces, you completely separate them, there's very low friction and no wear, the additive system won't give you that much of a benefit. Only in the mixed and boundary lubrication conditions, you will really benefit from the advantages of such an additive system. So it's a case-to-case basis. The 9% that we have seen earlier are real life values. So here we have measured the energy consumption in this component at the customer side with different oils. So we know what the customer was consuming. So 9% isn't any fictional number that was put in there. It's something that was really measured, energy consumption measured at customer side, and energy efficiency increases measured on customer side. But again, for your equipment, it might be different, higher or lower, and also, of course, depending on your design of your equipment and how efficient it already is. Just talking about design elements, the wheels, the cogs, the overall speed stages involved, etc. Phil, you wanted to add something?
Thank you, Marcus. Yeah, I think you've pretty much covered that. To add from a practical perspective as well, how would you measure energy saving then if you have so many variables? If you take good baseline readings, which could be from, if it's a three-phase motor, for example, take current readings of your current draw over a certain time period to cover seasonal variations too. Also, temperature readings of the gearbox. So temperature in the gearbox, you would expect if there's friction metal against metal that the temperature would rise. And we have seen this. There is a technical white paper that's in the public domain where it shows that the energy saving from a synthetic oil with PD type additives versus a conventional mineral oil, it can be in excess of 10 degrees temperature difference. So you'd expect a cooler running gearbox with a synthetic with PD plastic deformation additives. How would you measure that? You can purchase, they're like USB sticks that monitor temperature differences, and you can set them up from a laptop with maybe 1 minute intervals even. Leave it on top of the gearbox, collect it perhaps 6 months later, and that will give you your baseline readings. Same with the clip-on ammeters. You can find devices that you may have on site already that you can use to monitor that sort of performance and then compare with afterwards. To move on to the next question then, just looking at the time there, that we should be able to fit in the last two questions here. And thank you from Tim Vertriest. Is there an Optigear synthetic PD-ES equivalent of the Optigear 800-1500? If yes, would there be a reason to expect better performance? The application there is the bearings of rollers of a coal grinding mill. Thank you. So Optigear synthetic PD-ES is a synthetic group 4, which is polyalpha olefin type oil with the plastic deformation additives in it. Optigear 800 is a PAG, which is polyalkylene glycol. So they are different types of technology of lubricant. Now the 1500 there is the viscosity at 40 degrees. So this is a very high viscosity polyglycol product that's being used for these rollers, the bearings of the rollers in the coal grinding application. One thing that polyalkylene glycols are very good at is providing lubricity, and that's why you'd almost always see them in worm gears, because a worm gearbox between the worm and the wheel has almost 100% sliding friction, compared to a conventional spur type gears where you have sliding contact and then sliding friction. So it's a lot less on the sliding friction. Polyalkylene glycols are very good at giving the additional lubricity which is needed. So lubricity is one thing, load carrying capacity is another. And if it has a polyglycol with a base oil viscosity of 1500 centistokes measured at 40 degrees, I would think there's a reason for that, and it's probably to give a maximum amount of viscosity from a product that also has a very good viscosity index. Polyglycols, typically, the viscosity index might be 230 off the top of my head. So that means it's just a figure, but what it means is that the viscosity will be more stable over a wider operating temperature range. And if it's a coal grinding mill, it could be exposed to the elements, which might be -10 in winter and +30 in the summer. So you need something that has a good viscosity index. Optigear synthetic PDES, I believe, Daryl is on the call still, that goes up to 680 centistokes.
Yes, it goes up to 680. Yeah.
Thank you. Thanks.
You mentioned worm gear there, Phil. Sorry, just Optigear BM is the only mineral oil which has Flender worm gear approval. It's the only mineral oil on Flender worm gear approval due to that PD technology, due to that low friction.
Thanks, Daryl. Thank you. So, yeah, there could be, to answer your question, Tim, or at least in part, there could be an option to look at Optigear synthetic PD 680 ES. I would say that if we could be put into contact after this call, I'd be more than happy to look at that in more detail. So I hope that gives some thought towards answering your question there. Thank you. Good question. To go on to the last one that we see on the screen, we've got 3 minutes left, so that's quite timely. Is it always necessary to build a TCO, total cost of ownership proposal, if we want to replace the current lubricant with a plastic deformation product, or can we match only the viscosity? Yeah, it depends on the application. So if you have a gearbox with internal oil pump and spray system, yes, make sure that you do match the viscosity, because that's going to be very important. You don't have to build a TCO proposal or case every time. The important thing is just to make sure that it is documented why there was a change. Now, that change could have been because there's been an increase in production requirements, maybe speeds, loads have changed, and so on. It could be that new technology is now available, or it could be that consolidation of different products across the site means that there is also a change in a particular area. So not necessarily to build particularly a TCO study, but always important to document the change and to manage that change as well. Previous question was around changing from a polyglycol to maybe a Optigear synthetic PD. They are two different products and they are not compatible directly. So changing from polyglycol to a PAO, for example, you'd need something which has perhaps mutual compatibility. Thinking like a synthetic diester could be useful in that application. So you'd need to flush halfway through. So yeah, it's not always necessary in any case to build a total cost of ownership proposal or study, but replacing one lubricant with another, just think about why. Why is it being changed? What is the reason? What is the desired outcome of that as well? Viscosity is just one part of it. So I hope that helps a bit. Thank you. I believe we're up to the end of the time. So I'll hand over for the final wrap up. Thanks.
So I would like to thank the speakers for the session, and also I would like to thank all the attendees for attending the webinar. I hope see all of you next week on the same webinar regarding the high performance greases. I wish you have a nice rest of the day. Goodbye.